Hi guys, and welcome back to my channel. In this video I want to discuss intermolecular forces, and this is a topic you're probably familiar with, from general chemistry, but this video I really want to delve a little bit deeper into the sort of mathematical meanings of, the attractions. So for example, why is or how much weaker is a dipole-dipole force than an ion-dipole intermolecular force? These are terms you probably should have heard before. But I want to dive more into the mathematical relationships between the strengths of these forces. And specifically, I want to dive into potential energy graphs. So I want to be able to interpret, say I'm given a potential energy graph for a certain type of interaction and or two different types of interactions. I want us to be able to look at the potential energy curves and sort of deduce, okay, which one is weaker, which one is stronger, and why is this one weaker, why is this one stronger, what is it telling us about the forces in between the particles, right? So that's really my goal with this video, so let's just get right into it. Okay, so I just want to give an overview on what IMFs are and why we want to understand them, right? So these are intermolecular forces. That means between different molecules, right? So we have two different molecules or many different molecules, and there are forces in between them, and they're typically attractive forces, right? So why do we want to understand these forces in between molecules? Why can't we just understand the forces within a molecule, right? And figure out what just a single molecule looks like? Because we can't understand the bulk properties of materials. So our goal is to understand what we call bulk properties of materials in terms of the properties of the individual molecules themselves. So this should be, we're sort of like extrapolating here, right? We're saying, okay, let's look at a water molecule, for example. We see that there should be some polarity to this water molecule. We have a partial negatively charged oxygen, a partial positively charged hydrogen, right? So how does this affect, the interactions between water molecules as a whole? And then we can talk about dipole-dipole forces and how that, raises the boiling point and has all these interesting features, right? Hydrogen bonding. So our goal with IMFs is to take, to be able to understand sort of the bulk properties, right? Such as, cohesion, adhesion, all these things with water that we know and love, in terms of the properties of a water molecule itself, right? So we're trying to simplify this big problem down into a small problem, right? So we look to IMFs, the forces, which are the forces between molecules, and we describe these IMFs using the properties of individual molecules. And some properties we use, for example, are size, shape, and polarity. And in the case of water, we talk a lot about the polarity of water. Right? Water is polar, and that results in these strong hydrogen bonds between water molecules. But this is a key thing to understand, right? This is crucial to understand, is that IMFs are not the forces responsible for the formation of chemical bonds, right? They're not chemical bonding. IMFs are not, for example, the bonds that connect the hydrogen and oxygen in water, right, in a water molecule. We're talking about between water molecules. So they're not chemical bonds that form between atoms. These are between molecules, right, and they're just sort of weak attractive forces. So they're nowhere near as strong as an actual chemical bond. Okay, so now I just want to go over some basic terminology. This is a little bit, we should just know these terms. One term I want you guys to know is phase, right? What is phase? That's just a form of matter that is uniform throughout in both chemical composition and physical state. So this can sort of be confusing a little bit, right? We think of phases as just being like, for example, solid, liquid, gas, right? But this is describing only physical state. We can actually break this further down, right? I mean, technically there's plasma, etc. But these are the three main physical states, right? But we can break, for example, a solid down into different phases. So let's think about, carbon, for example. Carbon, in the solid phase, we have both graphite and diamond, right? These are two different examples of carbon in the solid phase. that have different chemical compositions, so different arrangements of the carbon atom. So this is just something to, some terminology to make sure you understand, is that phase is not the same thing as physical state. And then we talk about a condensed phase just being any solid or liquid phase. That makes sense, right? Condensed meaning that it's not gas. Okay, so now I just want to talk about sort of the basis for all intermolecular forces, and that is Coulombic attraction. Okay, so that is Coulombic, actually I wrote it here, Coulombic attraction. This is essentially what is responsible for all intermolecular forces. And we've seen this sort of Coulomb's law before, right? We've seen that force between two ions or two totally charged species is equal to K times the charge, Q1, Q2, both the charges, the product of the charges, divided by distance squared, right? That's the strength of the force between them, okay? So this also implies that the potential energy between two charges, right? So if I take two charges and bring them together, the potential energy of that system is equal to K, Q1, Q2 over the distance. Essentially, potential energy is equal to the integral of the force, or the force is equal to the slope of the potential energy. And this isn't, super important to know if you haven't had calculus exposure, but what is important is this 1 over d relationship that happens with potential energy when we have two ions, right? We have two full charges. Essentially, what we can do is we can describe all intermolecular attractions and we can trace that back to Coulombic interactions. Because basically, Coulombic interactions only describe totally charged ions, right? But we can sort of tweak our formulas to describe, for example, dipole-dipole. If we look at a dipole-dipole force, right? We have a positive on one side and we have a negative on the other side, but we know that these aren't full positives or full negatives. These are only partials, partial positive. So we have partial positive and partial negative, right? So just by intuition, we know that, okay, this force should be weaker than the force of two ions coming together, right? So our goal is to see what do we need to tweak in this formula, right? We know that we can't have Q1 and Q2 because those are full charges. So maybe we have something that describes the dipole moment of the molecule. How much, sort of what fraction is separated, right? What fraction of charge is sort of separated? And is it still dependent? Is it still proportional to 1 over d? Or is there a different proportionality that comes in? So that's our goal with the next slide, is to look at all these different interactions and see how we can tweak this general Coulombic attraction for ions, right? To describe dipole-dipole forces, dipole-induced dipole forces, all of these sort of different intermolecular forces. Okay, and finally, the next thing I want to do on this slide is to just get introduced and review potential energy diagrams. So here we have potential energy on the y-axis, and we have the internuclear separation on the x-axis, which is just how far are the nuclei apart. And there's three key things I want to discuss with this diagram. First, I want to discuss the minimums. So we can see, first of all, that the minimum of the IMFs, this is IMFs, the minimum potential energy for the IMFs is much, much, much higher than the minimum for covalent bonding or ionic bonding. Right? What does that mean? That means it's much easier to break intermolecular forces than actual chemical bonds, which makes sense, right? We can easily break IMFs by sort of vaporizing the substance and raising the temperature. But we need a really large amount of thermal energy to break chemical bonds, right? Chemical bonds don't just break when we form a gas. To form a gas, we're just breaking the IMFs. So it's much easier to break these IMFs than it is to break actual covalent bonds, right? And that should be, agree with our intuition, agree with our previous knowledge. The next thing I want to see is the distance the minimum potential energy is at. So if we look at the distance the minimum potential energy is at for IMFs, it's much greater than that of the chemical bond. What does this mean? And why does this make sense? This makes sense because what is participating in covalent bonds and ionic bonds? these are actual atoms and ions. Whereas with IMFs, these are intermolecular forces. We have molecules, right? So these atoms and ions can get much closer than molecules because molecules are much bigger than atoms and ions, right? So that's why our potential energy is at our minimum potential energy is at a lower distance for atoms and ions bonding than these weak intermolecular interactions, right? And the last thing I want to go over is you can see that below, when we start getting smaller than this potential energy minimum, you see both curves sort of like skyrocketing upwards to infinity. The potential energies are skyrocketing upwards. What does this come from? This comes from repulsions. So essentially, when we start pushing these atoms or ions or molecules too close together, we have these electron clouds overlapping. And when electron clouds overlap, you have negative charges getting close to each other. That's not very happy, right? Nothing likes the same charge coming together. So they push apart. And that's what creates this really steep increase in potential energy. Okay, so that's just how do we read a potential energy diagram and how do we understand what it's showing, right? So I just wanted to look at those three key things, and I hope that gave you some information on how do I interpret these diagrams. Okay, so on this slide, my goal is to just briefly explain the different types of IMFs, but more of describing how these IMFs, potential energies, relate to this potential energy diagram, and understanding how we can use this potential energy diagram to figure out stuff about the forces themselves. And the two main things I want to focus on are the strength of the intermolecular forces, the different IMFs, and the distances at which the IMFs really act, right? Those are the two sort of important things I want to look at with respect to the potential energy diagram. And so a key thing we have to know before we even look at potential energy diagrams is that force is proportional to the slope of the potential energy curve, right? So basically, the steeper the curve is, the more the intermolecular attractive force is. So for example, let's just take a point here. We see that this slope is slightly tilted, it's upwards, but it's not super steep, right? So if we look at this point at this distance r and we take the slope, and we look at this point at this distance r and we take the slope, we see that this lower separation has a much higher slope than this higher separation. And what does that tell us? That tells us that the force at this lower separation is much stronger than the force at the higher separation. And this affirms our general ionic, knowledge, right? That two ions have a stronger force when they're closer together, right? So that was just an example of how we interpret a potential energy diagram in terms of forces. And we're going to basically do that in this slide and look at all these different curves and compare the different curves in different ways, right? So I just want to briefly discuss every single or all the IMFs discussed on this slide. So we have ion dipole, dipole, London dispersion, right? You should have heard these terms before. Ion dipole is when an ion and a dipole interact. Dipole is two dipoles. London dispersion is generally two sort of non-polar molecules that are interacting due to their sort of instantaneous dipoles that are formed. So let's just talk about each one briefly. Ion dipole, the classic case is hydration. So this is when we have sort of a water molecule surrounding either a cation or an anion, and we can see in this picture, for example, the cation is surrounded by the oxygen parts of the water molecule because the oxygen parts are partially negative. The cation is obviously positive. And then the anion, it's reversed. We have the hydrogen parts pointing towards the anion, right? You should be familiar with this. This is kind of AP Chem review. But what I really want to focus on is the potential energy curves, right? We see that the potential energy for an ion dipole is proportional to the charge of the ion and the dipole moment of the dipole, right? So the charge of the ion tells us, okay, if it's higher charge, there's going to be greater attraction. There's going to be more lower potential energy. That makes sense. Greater attraction, right? So the higher the charge of the ion, the greater the attraction. And just one more thing I want to note is that when we have potential energy being proportional to 1 over r to, let's just say, to the k, right, where k is a number, the higher k is, the weaker the force is. So if we think about k equals 1, potential energy is proportional to 1 over r. This is the strongest intermolecular or strongest force we could possibly have, right? This is when we just have two ions, right? Two purely ionic full charges things, right? Like a sodium and a chloride, and we just have them attracting. That's a really, really strong interaction. That's when we have potential energy proportional to 1 over r. If we have, 1 over r cubed, or 1 over r to the fourth, or something like that, that's going to be weaker than 1 over r. If we had 1 over r cubed and 1 over r to the fourth, the over r to the fourth is going to be a weaker intermolecular force than the 1 over r cubed. So the higher, k is, that I just wrote down k, the higher k is, the weaker the force is going to be. So we can immediately see with ion dipole, we have the potential energy being proportional to 1 over r squared, right? So we see a weaker interaction than just a normal ion force, right? But this should make sense, because we don't just have two ions, we have one dipole, and a dipole only has partial charges, so it's not going to be as attractive as a purely ionic sort of thing. So to sort of reason this out, let's look at a little picture. So say we have a dipole with a plus and a minus charge, and we're looking at its interactions with a positive charge. And let's compare this to a purely ionic plus and minus charge. When we have purely ionic plus and minus charge, we only have this attractive force between them, right? Because opposite charges are going to attract. Whereas if we look at the dipole, we have the attractive force between the plus and the minus, but we also have a repulsive force between this plus and the plus, right? So we're going to have sort of a little less attraction than if we had two ions, because we have, we have our attractive force that is a weaker attractive force, because remember, this is not a full ionic negative charge, this is just a partial negative charge. But we additionally, on top of it being a weaker attractive force, we also have a new repulsive force that's added in, because there is a partial positive charge, right, that's going to repel. So that should make sense why our r on the denominator is to a higher power, making it a weaker attractive force, right? So that's what this means. 1 over r squared, that's going to be, this is a weaker attractive force than just a purely ionic interaction. So just another example of this idea of ion dipole interactions is we can see them with hydrated salts. So some salts, when they crystallize from an aqueous solution, they sort of retain these hydrating water molecules around them. And yeah, so that's just an example of these ion dipole forces at work. And the more highly charged and the smaller the cation, right? So if we have a really small cation and a highly charged one, that means that my potential energy and my force is going to be much higher, right? Because it's more highly charged and it's smaller. That makes my distance smaller, which means that my force is going to be greater, right? So the more highly charged and smaller, the greater these attractions are and the more extensively hydrated they are, because the stronger the ion dipole forces will be. So that's just an example of, ion dipole forces that work. Now let's look at dipole-dipole forces. So we can think about dipole-dipole, we intuitively think should be weaker than ion dipole, because with ion dipole we have at least one full ion. Dipole-dipole, we don't have that one full ion, right? So we should have r to an even higher power. And we do see that because we have 1 over r cubed. We have potential energy proportional to 1 over r cubed, which means that the force is even weaker than the ion dipole, right? And let's see on the top, what is it proportional to? We don't have any full charges. So if we remember, like in ion dipole, we wrote Z as the charge of the ion, but we can't write Z in dipole-dipole interactions because there are no full ions. Instead, we write the dipole moments of the two dipoles, right? And we call these dipole moments mu1 and mu2, and the dipole moment just sort of quantifies how polarized this molecule is, how much there is a partial positive or a partial negative charge. Okay, And this should make sense that we have 1 over r cubed. It should be weaker than our ion dipole. And if I draw it out, say we have a plus minus and a plus minus, we have our two attractive forces, right? The minus and the plus on both the dipoles sort of attracting each other. But we also have the two repulsive forces with the plus plus and the plus minus, or sorry, the plus plus and the minus minus repelling each other. So we have these now these sort of two weak attractive forces, and also two repulsive forces, right? So that should make it an even lower sort of attractive force between these dipoles, right? And that comes in the r cubed term that we see on the bottom. Okay, and additionally, if we look at rotating polar molecules in the gas phase, we see that the potential energy is proportional to mu1, mu2, right? The dipole moments, the product of the dipole moments, but over r to the 6th, right? That's kind of weird, right? Why is it so much lower, right? Why is the attractive force so much lower? That's due to because they're in the gas phase and they're rotating. So when these polar molecules are sort of free to rotate in the gas phase, these dipoles will never actually align. They won't, like, for example, when we have dipoles in the liquid phase or the solid phase, we have plus minus, and we have these dipoles aligning, so we have like a minus attracting to the plus, and another plus, like something like that, right? But in the gas phase, these are all rotating and they're all jumbling apart, and none of these can actually align. The dipoles can't actually align, and that just means the attractions are basically the same as these weak London dispersion forces that just arise from instantaneous dipoles, right? And London dispersion forces fall off as r to the 6th, which I'll show in the next bullet point, right? Okay, so essentially when we have rotating polar molecules, they just look like London dispersion forces because there's no dipole alignment. And finally, we look at London dispersion forces, and we see the potential energy is proportional to 1 over r to the 6th, right? This makes sense. That's what I just said. And it's much, much weaker than dipole-dipole, for example, right? Which makes sense because these are just sort of instantaneous random dipoles that are forming in certain times, and it's not like an actual dipole of the molecule that's contributing to these intermolecular forces. And on the top, we don't see a dipole moment anymore because these molecules don't have a dipole moment, right? There's no like actual dipole in this molecule. Instead, we have alpha 1 and alpha 2, where these are polarizabilities. And you should have heard of polarizabilities before. A polarizability just increases with the number of electrons that the molecule or atom has. All it means is that the more electrons, the more probable that these instantaneous partial charges will form. And so there'll be a higher potential energy or a lower potential energy and a stronger attractive force, right? The more polarizable the molecule, the stronger the London dispersion forces will be. And the effectiveness of London dispersion forces also actually depend on surface area. So if we think about, something with a lot of surface area, the more surface area that you can sort of, that molecules can come in contact with, right? So if we have more surface area where these molecules can smush together, there'll be more attractive forces, right? So why? Because if we have more surface area that can come together, that means there's more places for these molecules to attract each other, which means that there should be stronger London dispersion forces. So London dispersion actually doesn't just depend on, the dipole itself or the polarizability, but it also depends on surface area, which makes sense because we're just looking at random instantaneous charges. So if there's more surface area that these molecules can interact, we're giving sort of more probable chances that there will be an instantaneous charge at one of those positions, and therefore there will be an attractive force at one of those positions. Okay, so now I want to take what we've just, we talked about a lot, and I want to look at this in terms of a potential energy graph, right? So this is what I really want, that I think is important to see, right? So the first thing we see is if we take some random distance, let's look at r here, like we take some random distance r, and we look at, the slopes at each of these r's. Go up, take the slopes, take the slopes, take the slopes. What do we see? The slope of the 1 over r curve is much greater than the slope of the 1 over r squared, is greater than the 1 over r cubed, is greater than the 1 over r to the 6th. This makes sense. This is what I've just been talking about all along, is the lower the denominator power is, or the higher the denominator power is, the weaker the intermolecular force, right? Because the smaller, the less steep the slope is. So 1 over r sixth means weakest force, right? This is what I've been talking about all along, but I just want to describe it in terms of a graph, right? And the second thing I really want to look at is the distances at which these forces really start happening, right? We can see this sort of elbow for all of these curves, where below this elbow, right, to the left of this elbow, we see a much steeper part, and to the right, we basically see it's essentially flat. We can see this elbow sort of moves to the right with each curve, right? So with 1 over r here, this elbow is much further to the right than the 1 over r to the 6th. And what does that tell us? That tells us that essentially where the 1 over r force starts attracting to a significant amount is at a much further distance than the 1 over r to the 6th. So, for example, London dispersion forces only really act at really small distances, whereas ion forces are going to act at much larger distances. All right, so on this side, I would just want to wrap up the types of IMFs that I talked about on the previous slide, but, other IMFs. We should have heard of dipole-induced dipole, van der Waals, and hydrogen bonding, right? These are all classic IMFs that we learn. So first of all, let's look at the potential energies for dipole-induced dipole. We see that the potential energy is proportional to, we have mu1 squared alpha 2. So mu1 is the dipole moment of our dipole. Alpha 2 is the polarizability of our, nonpolar substance, that is the polarizability of our nonpolar substance that is, participating in the that is having its dipole induced, right? So an example of this is we have water and we have oxygen dissolving in water. Oxygen itself is nonpolar, but when we have oxygen dissolving in water, a dipole is sort of induced in the oxygen by the water molecule and forms these attractive forces. So we can think about it like this, right? We have our water molecule that has a negative charge, and we have our water molecule that's going to have a slight positive charge next to the slight negative charge oxygen. The negative charge oxygen of the water is going to induce a dipole in that in the oxygen molecule, such that there's an attraction, right? And we can see what's interesting is we have mu1 squared, right? We don't just have mu1. Why do you think this is, right? Because mu1, first of all, you have the factor such that that dipole is going to interact with the other substance and form an attraction, right? But you have the other factor, which comes from that dipole. The strength of that dipole actually causes the strength of the other dipole, right? So this is sort of a weird thing to think about. Is our first mu1 is the dipole itself, right? The attractive forces coming from the dipole itself. The second mu1 is the attractive forces coming from the inducing of the dipole of the other substance, right, of the other molecule. And the alpha 2 tells us how easy is it to induce a dipole. So if we have higher alpha 2, that means it's easier to induce a stronger dipole in that, for example, oxygen molecule. If we have higher mu1, that means not only higher attraction because this guy is more charged, but a higher induced dipole because that charge is causing the dipole of the other nonpolar substance. So that's why we have these two sort of factors of mu1, right? And the next thing to notice is that our potential energy is proportional to 1 over r to the sixth. So we know this is a weak interaction, right? This is a London, sort of as weak as just a normal London dispersion interaction in terms of its relationship with distance. But obviously it's stronger because we have these mu1 terms involved, which are, actual fixed dipoles, right? Not just polarizabilities of two nonpolar substances. And then we have van der Waals forces, and this is sort of just like an umbrella term, right? Van der Waals forces are any interaction where we have the potential energy being proportional to 1 over r to the sixth. And this includes, we talked about London dispersion, it includes rotating polar molecules in the gas phase, and it also includes our dipole-induced dipole. So all of these, where we have 1 over r to the sixth interactions, we just call it van der Waals forces. That's just a terminology thing. And finally, we have hydrogen bonding, and this is a classic, right? We should know this. These are extremely strong bonds, and they're typically 10% of covalent bond strength. So this is like really strong, right? And what is a hydrogen bond? This is like when you have a hydrogen atom bonded to a small, highly electronegative atom like nitrogen, oxygen, or fluorine. And these sort of positively charged hydrogen atoms, because of the polar nature of that bond, are going to be attracted to lone pairs of electrons on other nitrogen, oxygen, or fluorine atoms. So, for example, there's two examples of this that I know of is formation of these hydrogen fluoride chains and also acetic acid dimers. So these are just examples of hydrogen bonding at use. And obviously we know hydrogen bonding is in water and stuff like that. But some more interesting examples are these dimers that are formed when we have acetic acid, because you can see that this lone pair on the oxygen is attracted to this hydrogen. So we have this like bond this hydrogen bond being formed there, and we also have this lone pair on that oxygen being attracted to the hydrogen, right? So we have a different hydrogen bond, and this forms like a dimer. It dimerizes, right? Two of these molecules, acetic acid molecules, can come together and form and sort of lock together because of that hydrogen bonding. Additionally, we have the formation of HF chains, and that just means, say we have HF, then this electron, right, an electron pair on this HF, will form a bond with another, or a hydrogen bond with another HF molecule. So we have something like this, where we have this is a hydrogen bond, right, and this chain can keep going on and on and on, and this is due to, the hydrogen bonding of H and F, right? And hydrogen bonding is incredibly important in biological systems. This is what keeps DNA strands paired together. So if you've heard of like ATGC, that's what keeps the A and the T and the G and the C sort of together, locked together. And, hydrogen bonding also governs the shapes of proteins, so it's incredibly important in biological chemistry. But I just wanted to, give some examples of where hydrogen bonds are important. Okay, and finally, I want to talk about repulsions. So we talked initially, or a little bit before, about how when we sort of went below, when we took, two atoms or something and went to a radius or a distance that is smaller than the minimum potential energy, we saw how the curve sort of skyrocketed up. And I said this was due to electron clouds being forced together and these repulsions that come from the electron clouds being forced together, right? So that's essentially what is happening with repulsions. When two molecules get super close to each other, they're going to repel. And I just want to take a really simple case of, for example, helium-2, right? Helium is a noble gas, so it's very, happy and stable. It likes just being helium, right? But say we smush these heliums together so much that they end up almost like forming a bond, right? Their electron clouds are overlapping, and therefore they're almost like forming a bond between two heliums. What does that look like in terms of molecular orbital diagram? So if you remember molecular orbital diagrams, we have our 1s orbital on helium, and it's filled with 2 electrons, right? And when we push a s and an s orbital together, we form a sigma bonding orbital and a sigma star anti-bonding orbital. So we would form a bonding orbital that's slightly lower in energy and an anti-bonding orbital that's higher in energy. And if we fill these guys up, there's 2 electrons on each helium, so when we have the total molecule, we should have 4 electrons. We see that there's 2 electrons on the sigma, the bonding orbital, but there's also 2 electrons on the sigma star anti-bonding orbital, right? And remember that anti-bonding orbitals are actually slightly higher in energy than those bonding orbitals. So what's important to note from this is that helium-2 is actually less stable. It's higher in energy, less stable than just having helium atoms, right? And we can extend this idea to molecules, right? So essentially what I wanted to get from this example is when, two happy molecules or 2 happy atoms like helium come together and they form like a quote unquote bond, it actually raises the energy based on this molecular orbital theory. And that's how repulsions sort of come about, right? When 2 molecules get close together, they essentially form, this is very colloquial language, but molecule 2, right? Like how I said helium-2, it's like molecule 2. And just like with helium-2, this is going to be less stable than the molecule itself, and therefore we're going to have repulsions because it's not going to want to come together. So that's the sort of origin of these repulsions, this electron clouds overlapping that causes these repulsions. All right, so this is all I sort of wanted to cover with this IMFs video. It was a lot of information, but I hope, you were able to learn how to, read potential energy diagrams and get a better understanding for the quantitative notion of how strong and how weak these IMFs are in comparison to each other. Thank you guys so much for watching, and I'll see you in the next one.